Welcome everyone, I'm Bené Duncan with the Western Water Assessment at the University of Colorado Boulder. Thank you for making time in your schedules to join us for this webinar, which will provide an overview of the recently released report, Colorado River Basin Climate and Hydrology, State of the Science. We'll have a presentation of about 30 minutes, and then we'll use the remaining time for questions. Between the presentation and questions, we'll have a very quick survey to get your input on future topics for webinars based on the report. This webinar will be recorded and the video will be available on our website, www.colorado.edu. We'll be sure to share that link with you after the webinar. Before we get started, I wanted to share a bit about Western Water Assessment for those of you who have not worked with us in the past. Western Water Assessment is an applied research program that addresses societal vulnerabilities to climate variability and climate change, particularly those related to water resources. While we are based in Boulder, Colorado and Salt Lake City, Utah, we work across the Intermountain West, which includes Colorado, Utah, and Wyoming. Western Water Assessment is one of 11 teams in the NOAA Regional Integrated Sciences and Assessments, or RESA program. During today's presentation, you can ask questions with the Q&A chat window. We will save any questions that come in during the presentation and answer them during the Q&A period. Now, I'd like to introduce Jeff, Lukas, and Liz Payton, who were the co-lead authors and editors of the report. Jeff will start us off, and then Liz will jump in.
Thanks, Bené, and thanks to everyone for joining us. The future is, and always has been, uncertain. So water managers in the Colorado River Basin produce and consult forecasts of reservoir storage and other system conditions at short-term and mid-term timescales, and also long-term system projections. For the short term, this identifies a most probable future, and at longer timescales, it places some bounds on the uncertainty and defines a range of plausible futures. Now, at a time in which the basin's water supply and depletions are in delicate balance at best, and the system storage is half full, and climate change is increasingly impacting hydrology, these forecasts and projections have become even more critical. Further sharpening these outlooks and reducing the uncertainties where possible can help in managing a stressed resource. The past decade has seen hundreds of new research studies relevant to the climate and hydrology of the basin and the data sets and models used to inform basin water management. The most relevant applied research efforts were presented at the 2017 Colorado River Hydrology Research Symposium in Las Vegas. Expansion of the scientific knowledge base has come with increasing complexity of the data and models used to operationalize the knowledge. The symposium participants saw the need to synthesize the current state of the science and technical practice that supports the management of basin water supplies. In 2018, a work group of state water agencies, municipal water utilities, and water districts across the basin, and the Bureau of Reclamation approached us to develop a science synthesis report for the basin. This work group had been organized to advance scientific understanding of the basin to improve hydrologic forecasts and projections. Its members had helped convene the 2017 symposium. In addition to funding and guidance from these sponsors, we also received substantial technical assistance from the NOAA Colorado Basin River Forecast Center, CBRC, and also from the USGS. And now let me hand it over to Liz.
Thanks, Jeff. Several objectives guided the report effort. First, to synthesize the relevant science and technical practice at short-term, mid-term, and long-term timescales. Second, to convey knowledge gaps and uncertainties in such a way as to prompt research ideas and inform priorities for funding. Third, to inform the scientific community about reclamation models. And finally, by providing this information, to serve as part of the scientific and technical foundation for renegotiation of the Secretary of the Interior's 2007 interim guidelines for lower basin shortages, and the coordinated operations for Lake Powell and Lake Mead. To be both useful and tractable, the synthesis report needed some boundaries. The report does not evaluate current basin operations and policy. It identifies opportunities for research and improvements, but without making specific recommendations. Its primary focus is water supply. Water demand and water use do enter the discussion, but are not treated in depth. Other important basin management issues, such as water quality, fisheries, ecosystem management, and sedimentation, also fall outside the report's boundaries. We worked with an excellent team of individuals who are experts in the topics covered in the report. Many of the authors are researchers from the University of Colorado here in Boulder, and our author team also includes scientists from NCAR, the University of Nevada, and the University of Arizona. Water resources engineers from Reclamation made significant contributions to the text as well. In addition to the contributions by this team, we sent the first draft of the report out for peer review by subject matter experts who generously took the time to offer critiques and suggestions. Members of the work group also provided critical comments on draft versions of the report.
The organization of the report by volume and chapter generally follows the flow of information that supports the management and planning of water supply. It starts with our current understanding of patterns, processes, and trends at top in pink, then moving on to the primary data and models, which are based on observations of climate and hydrology in blue, which then feed into the short-term and midterm forecasting tools for weather, climate, and stream flow in green, as well as the development of hydrologic traces for long-term planning in yellow. Finally, the short and midterm forecasts and the long-term hydrologies are used as inputs to the three primary reclamation operations and planning models. In the report, these system models are described early on in chapter 3 to provide context for the subsequent chapters. Now we will walk through chapters 2 through 11 that lay out this chain of models and data. We can't possibly do justice to a 500+ page report in a single webinar. Many of you on this webinar we know are bona fide experts on these topics, while many others of you may have only a passing familiarity with the basin. But we will try to give everyone a better sense of what is in the report and encourage you all to explore it in greater depth, while conveying at least some of the key points and challenges and opportunities from the full report. First off, understanding the spatial and temporal variability of the basin's hydroclimate underpins how we collect and use observational data and develop the modeling and forecast tools. The past variability and recent trends also help frame expectations of future basin hydrology even before we consult the tools that are explicitly designed for forecasting and projection. Historically, year-to-year variability in Colorado River stream flow at Lee's Ferry has been primarily driven by variation in upper basin precipitation, as shown in the two traces here. In the most recent decades, that strong relationship is still apparent, but another influence on stream flow has been increasingly asserting itself: temperature. In effect, temperature is opening up a gap between precipitation and stream flow. In the past 40 years, a warming trend of about 2 degrees Fahrenheit has discernibly impacted basin hydrology. This regional warming, like that at broader scales, has been linked to human causes. Since 2000, a period of slightly below normal precipitation in the basin has been exacerbated by higher temperatures, leading to even lower snowpacks, earlier runoff, and lower stream flows than would have occurred in the absence of warming. Several recent studies indicate that 20 to 50% of the observed cumulative stream flow deficit since 2000 at Lee's Ferry is due to the warmer temperatures.
One of the report's goals is to inform the scientific and water management community about the 3 primary reclamation system models and how they support operations and planning and related research efforts. 3 monthly reclamation models developed in Riverware support planning at 3 timescales as shown in this figure from Reclamation. Short term up to 24 months, midterm up to 60 months, and long term spanning multiple decades. The models are the 24-month study or 24MS, the midterm probabilistic operations model or MTOM, and the Colorado River Simulation System or CRSS. The 3 models are used to simulate and analyze Colorado River system operations under various scenarios of hydrology, demands, and policies, as shown in the figure. Limitations in these models arise from necessary simplifications of a complex water supply system, and uncertainties arise from input data sources and assumptions about the future. These maps show the inflow points for 24MS, MTOM, and CRSS. Hydrologic inputs to the short-term and midterm models shown on the left are either monthly flows forecasted by the CBRC or average monthly flows depending on how far out in time from the starting month. For some applications, the forecasted end-of-year reservoir conditions from these shorter-term models are used to initialize the longer-term CRSS model. Hydrologic inputs to CRSS may be based on historical hydrology, paleo hydrology, climate change informed hydrology, or hybrids of these hydrologies. Much of the remainder of this report is devoted to explaining how these hydrologic inputs are derived.
Weather and climate observations are the first of those input sources examined in the report. These observations are central to understanding, modeling, and forecasting basin hydrology. Increasingly, they are processed into spatially gridded data products before being input into a forecast model or otherwise used. Gridded climate data products have brought major benefits: more spatially sophisticated analysis, modeling, and forecasts. They also put a greater burden on users in selecting an appropriate gridded product, since they draw from different but overlapping sets of station data and employ different processing of those data, as this diagram shows for several gridded precipitation products named in the boxes at the bottom. And the gridded products inherit the limitations of the underlying station data, especially the lower density of observations as one goes back in time and also at higher elevations. This caveat applies to any gridded or spatially distributed data set. Just because there's a value for every pixel doesn't mean that every pixel is equally reliable.
Like weather and climate observations, hydrologic observations such as snowpack, streamflow, and soil moisture are key inputs to basin streamflow forecasting and system modeling. For snowpack observations, the snow net shown in the map on the left is essential to monitoring and streamflow forecasting. However, point measurements are not dense enough to fully represent spatial variability across the basin and aren't necessarily cited to optimally inform streamflow forecasts. Spatially distributed snowpack data from models and remote sensing are therefore increasingly used to augment SNOWTEL data. Soil moisture observation locations are in the map on the right. In situ measurements of soil moisture and evaporation related variables are especially sparse, so spatially distributed data from models and remote sensing have an even larger role to play in estimates of variables. Flow naturalization methods try to estimate what the stream flow at a gauge would have been without the impacts of upstream human activity. To develop the monthly flows for input to CRSS, Reclamation makes adjustments to the gauge stream flow data at CRSS inflow points for upstream reservoir operations and consumptive use. The figure shows gauge flows and Reclamation's naturalized flows for the Colorado River at Lee's Ferry over the period 1922 to 2018. The gray difference line is the net adjustment made to estimate the natural flow.
Hydrologic models, which simulate watershed processes and outputs like runoff, are used in a broad range of applications in the basin. The applications most relevant to basin water supply management and planning are stream flow forecasting and climate change projections. As with other geophysical modeling, the leading edge of hydrologic modeling has been moving towards greater complexity and higher spatial and temporal resolution. But increasing model complexity does not guarantee improved performance for all applications. Shown here is a schematic of the hydrologic model behind the CBRC water supply forecasts, SAC SMA. Notice especially the partitioning of the subsurface water into 5 buckets at the left, and how they contribute to the flow hydrograph at right. SAC SMA is actually a relatively simple model, but it has proven itself to be an adaptable and reliable forecast tool. But for translating climate model projections of temperature and precipitation into stream flow, a more fully physical land surface model like VIC is generally better. On the other end of the spectrum is a rapidly emerging hydrologic modeling approach that uses machine learning methods such as artificial neural networks that are trained only on observed data sets. Such models operate by essentially inferring the runoff processes shown here without explicitly representing them. The uncertainty about upcoming weather and climate conditions translates into a significant source of error in seasonal water supply forecasts. As we saw in 2015 and also this year, the weather that occurs after the key April 1st forecast date can have a substantial impact on the seasonal runoff. Forecast skill means the accuracy relative to a no-knowledge forecast, such as the historical average. In this schematic, we see that weather forecasts shown in red have relatively high skill, though it rapidly falls off with time. CBRC's water supply forecasts do incorporate weather forecasts out to 10 days for temperature and 5 days for precipitation. But sub-seasonal and seasonal climate forecasts, shown in purple and blue, are a different beast altogether. They rely on weaker sources of predictability and have much lower skill than weather forecasts, especially for the upper basin. CBRC does not currently use them in water supply forecasts, and recent explorations to do so have not been very successful. But there is a major national and international research program to improve climate forecast skill at these longer timescales, including some regional efforts. There are also strategies being developed to better deploy the limited climate forecast skill that does exist. But we should not expect to be able to treat climate forecasts like weather forecasts anytime soon. Seasonal stream flow forecasts from the CBRC comprise much of the inflow inputs to the 24-month study in MTOM operational models. The ability to predict seasonal stream flow in the basin arises almost entirely from capturing what are called the initial watershed moisture conditions, soil moisture, and especially snowpack. In the past several years, CBRC has increasingly relied on ensemble streamflow prediction, or ESP, forecasts from the SAC SMA hydrologic model to guide the monthly and bi-monthly official streamflow forecasts. ESP forecasts are also issued as daily products. The spaghetti of the ESP forecast traces at the right reflects that uncertainty in the upcoming weather and climate. For most gauges in the basin, the median ESP forecast is now more skillful than statistical water supply forecasts that had been the benchmark for decades. The last 3 chapters of the report are devoted to 3 complementary perspectives on basin hydrology that together help shape expectations for future hydrology at the long term for planning purposes: the historical hydrology, paleohydrology, and climate change informed hydrology. The most recent basin planning studies, starting with the 2012 basin study, have examined system performance under all three types of hydrology, and each type brings important characteristics to the table.
The observed historical streamflow record is used to generate streamflow traces for input to system models for long-range planning, as well as to validate and calibrate paleohydrology and climate change-informed hydrology. For decades, the index sequential method, or ISM, has been the most common method used in reclamation system analyses of historical hydrology. ISM has advantages, but also significant limitations, most of which center on the fact that ISM traces do not deviate from the observed historical record. This figure shows ISM applied to the full historical record in blocks of 42 years advancing 1 year per trace. ISM preserves the historical sequence and range of streamflows, but cannot generate event magnitudes, durations, or frequencies outside the observed record. Stochastic hydrology approaches have been and are still being explored as ways to generate novel streamflow traces. Current efforts are also focusing on methods to impose non-stationarity on the historic record while retaining many of the characteristics of the observed streamflows. Reclamation has explored applying ISM to segments of the observed record other than the full historical trace. Most recently, in response to an extended drought and the need to support drought contingency planning efforts, Reclamation and stakeholders in the basin identified the period from 1988 to the present as a period that could provide a different perspective on system risk because it does not include the extraordinary wet years of the early part of the historical record. This sequence of years is referred to as the stress test hydrology and is compared to the full record in the figure. Multiple other methods have been used by Reclamation and others to generate Colorado River Basin streamflow traces from the historical record for system analysis, including hybrids with paleohydrology and climate change-informed hydrology, but none has yet emerged as a clear best choice.
Expectations for the future hydrology of the basin are also informed by paleohydrology records developed from moisture-sensitive trees. These streamflow reconstructions effectively extend the observed hydrology back in time, expanding our perspective of the natural variability in streamflows. Over the past 40 years, researchers have developed several streamflow reconstructions for the Colorado River at Lee's Ferry, with the more modern reconstructions shown in the darker colors increasingly converging on very similar depictions of past dry and wet periods. Two features stand out. First, the 20th century was unusual in having two multi-decadal wet periods, or pluvials, the first in the early 1900s and the second in the 1980s and 1990s. Second, the pre-1900 period shows severe sustained droughts that are worse than any experienced during the 20th century or thus far in the 21st century. The longest tree ring reconstruction for Lee's Ferry, going back over 1,200 years, amplifies that second point. The orange shading highlights several multi-decadal dry periods that affected most of the Western US and have been given the name megadroughts. This tells us that the natural variability alone can lead to reduced streamflow over long periods, up to 60 years in the case of the megadrought in the 1100s. A new research study that was released after the report came out indicates that the scope and magnitude of overall arid conditions since 2000 over the Western US are actually comparable with some of these ancient megadroughts. Finally, climate change-informed hydrology has been used in recent basin planning studies to complement these other sources of long-range hydrologic information. These model-based projections, unlike the other two sources, explicitly account for human-caused changes to the atmosphere and the climate system going forward. But the complexity of the data and the broad range of potential future outcomes can be frustrating to practitioners and researchers trying to work with the projections. Most methods developing this information start with global climate models, GCM in the orange box at top, driven by different emission scenarios. These methods, 5 of which are shown with the respective colored arrows, incorporate multiple steps of processing with corresponding choices that each have implications for the final output and its uncertainty. As with many areas covered in the report, there is no but one best way to do the job. There is a different but complementary approach, which is to essentially start at the bottom of the diagram and identify system vulnerabilities before querying the climate projections. Regardless of the approach used, one sees recurring themes in the projected hydrologic outcomes, here focused on the upper basin. For those who know and love the acronyms, this is a new data set of CMIP-5 climate projections that were run through LOCA downscaling and then to produce stream flows, the VIC hydrologic model. The upshot is that basin temperatures at top increase across all model projections, while annual precipitation in the middle goes up in some projections and down in others, while showing generally increased interannual variability. At the bottom, the pervasive effects of warming effectively tip the ensemble downward so that in most of the individual projections of stream flow, future runoff at Lee's Ferry is reduced. To summarize, across the different areas and timescales covered in the report, scientific advances have led to many recent improvements in the various links in the chain of models. The report also identified many further opportunities to improve the data and models, falling into broad pathways that are listed here on the left. There are ongoing efforts in all of these areas, many involving Reclamation and the other report sponsors, and also CBRFC. Their continued involvement in research is critical to facilitating the difficult transition from research to operations. So it is reasonable to expect that even incremental progress along each of these many paths will result in more accurate system forecasts over the next several years. But large uncertainties, especially at the midterm and long-term timescales, will undoubtedly persist. So the use of operational and especially planning approaches that better accommodate uncertainty will be increasingly important in supporting good decision-making. Finally, while scientific advances do help close knowledge gaps and reduce uncertainties, the routine, even mundane observations of weather and hydrology are still fundamental to understanding and predicting the climate and hydrology of the Colorado River Basin.
Great. Thanks so much to Liz and Jeff for this presentation. The report is packed with information, so I think it's really helpful to have had this guided tour. Thanks also to those of you who have already submitted questions through the Q&A box. We are going to be transitioning to question and answer, so please keep those questions coming and we will answer as many as we can. But before we transition to the question and answer period, we wanted to get your input on what topics from the report are most of interest for future webinars. So I'm going to display a very brief poll that should take you no more than 30 seconds to answer. And we'd love for all of you to participate in it if you can. So give me just a second and I will get this poll listed. Okay, and then you should all see a poll in just a moment. And so now, if you could just answer this one quick question for us, that would be much appreciated. And in the meantime, please submit your questions as well. It looks like just about 7% of you have voted so far. So if folks could just take a quick second to answer this pop-up poll question that should have appeared on your screen, then that would be great. Oh, look at that. Now we're getting a ton of responses. Thanks so much, everybody. In just a moment, I'll close that poll and we'll show everybody what the results were, and then we can move on to the question and answer. Okay, and I will end that poll now and we can move on to the question and answer. We'll share the results as well. You all should be able to see the results. It looks like a majority of you are interested in hearing more about hydrologic data, and then also an overview of the climate and hydrology of the basin and a focus on recent trends, and then climate change informed hydrology for long-term planning. And it looks like there's interest in all of these categories. So that's wonderful and very helpful for us. So thank you all so much for participating. With that, let's switch over to the question and answer. We've got a few questions here. Let's see, the first question that we'll ask is, let's see, Patrick Shea has asked, did you have any elected or appointed public officials participate in the formulation of the synthesis? So I'm not sure, Liz and Jeff, if you wanted to maybe speak a bit about the work group that helped pull this report together.
Sure. So I think that the short answer is no, not directly, but to the extent that we had over a dozen public agencies involved who have, boards and are responsive at the, local, state, and federal level to both appointed and elected officials who oversee their agency's actions. I'd like to say that, their input was responsive to or mindful of the needs and interests of those officials.
Great, thank you. Let's see, we've also got a question from Joel Smith, who's wondering if we have any preliminary insights on what CMIP-6 climate models are projecting for change in climate and flow of Colorado River.
Yeah, thanks, Joel. That's even though the CMIP-6 latest generation of climate model results have been coming in as we were writing the report, they're not fully out and explored in the literature yet. But we do have, I think, a few paragraphs about CMIP-6 in the report and in chapter 11. They so far have not been analyzed, at the scale that would let us say, how they would look different in terms of outcomes like projected future stream flow for the basin relative to CMIP-5. What I've seen so far says probably not much different. There seems to be a little greater temperature sensitivity in the CMIP-6 models that is showing a little higher, global temperatures in the future for a given emissions scenario. So that may, have some bearing on runoff projections, but it's a little too preliminary to say exactly what it's going to look like for our region.
And we've got another question that relates to stream flow, and that is, can you tell us your findings of stream flow reductions?
So I'm not sure exactly what time scale this is referring to. Um, I could say if we're talking about future projections, then there's a range of reductions and actually some plausible futures that show increasing stream flows. But the majority or even the large majority of future projections based on climate models of Colorado River stream flows at Lee's Ferry and also for the lower basin show reductions, and those reductions are anywhere from 5 to 30 and even up to 50% with ones associated with higher emission scenarios like RCP 8.5 and later, those projections for later in the century showing larger reductions. So I think for more detail, I'll just have to refer you to chapter 11 in the report.
Great. And let's see, I think the next question we could answer, we've got one question that says, for the general public, what would you say the chief takeaway is? Would you say it's the slide with the temperatures, the precipitation, and the stream flow graphs, or what? And so I wonder, Jeff and Liz, if you could speak to just kind of chief takeaways for the general public from this report.
So I actually, because we hear about so many studies that forecast and reasonably so, fairly dire futures for the Colorado River. Yes, we've got content in here that comes from the scientific literature that shows those can show some grim projections, but I think the bigger meta message of this report is that we've got this great collaboration among water agencies across, but in both the upper and lower basin, working together to gather more information about the past, the present, the future of climate and hydrology in the basin in order to make better decisions and do better planning. And so that, I think, is the story I'd like to emphasize, and sort of the overall improvement in the tools and our ability to look forward and to manage the basin.
Great, thanks, Jeff. Let's see, I think kind of building on what you were just talking about, we've got a question that says, have you seen or heard how people are using this report or plan to use it? How do your groups anticipate building off of this work? So maybe you could speak a bit to some of the initial use or how folks plan to use the report from what we've heard.
Yeah, that's a great question, and something we had in mind throughout the report, having input and guidance from our sponsor agencies throughout the process. And we actually did a survey. Our undergraduate intern, Ethan Knight, surveyed our sponsors to kind of get an initial beat on how they were expecting to use the report. And I think I can't speak to how that's panned out over the last few months and exactly how it will be used in the future. But I think in a couple of different ways, to help with some of the higher level messaging, help educate and inform their agencies stakeholders. So everything from their boards to their publics and ratepayers, to inform internal discussions about how they should set up and run their own system modeling and planning exercises that go on within each agency. And then finally, to help inform and serve as a foundation for basin level discussions, whether it's renegotiating the interim guidelines or looking at other trans-basin issues that they're involved in. So I think to serve as sort of a reference, a kind of an information or research backstop to a lot of conversations at different levels.
We did receive a fair amount of feedback already, and folks are expressing appreciation for the reference sort of aspect of the document, that because we put in so many links to sources and places they can download data and models, and we looked at over 800 papers and studies, and and all of those are in our references. So it's as a document that people can just pull off the shelf and find out, how is this particular data set assembled, or what are the inflow points for this particular model, that kind of thing, as a reference that everybody can be working from, has been one of the goals, and it seems to be sort of the way people are using it.
Great, thanks Liz and Jeff. Let's ask a really more technical question that we've received, which is about cell size in the models and how they account for the huge elevation changes in the upper basin. Could either of you speak to that at all, the cell size in the models and how they account for the huge elevation changes in the upper basin?
Yeah, so that's a great question. It applies to all sorts of models and gridded data. Is, how fine a resolution do we need in order to realistically portray the incredible topography of both the upper and lower basin, and then through that to appropriately represent the processes that are driven by or influenced by topography. And I'd say that a lot of the modeling is being done at a scale that it really shows realistic mountains, and that might be 25 kilometers or less as a cell size or grid size. Some of the gridded products are now down to 4 kilometer or even sub-kilometer models, like the hydrologic models, typically run at, like a, 12 to, 6 kilometer grid size, things like Vic. GCMs are still kind of, they're improving in resolution, but they're still kind of the outer bounds of what they can natively show in terms of topography, which is why we have to downscale climate model output to that much finer resolution, like a 25 or generally more like 12 kilometer grid size. So yes, you do need fairly small cells, particularly the global scale climate models are not quite there in their native output, but most of the other models and data sets, spatial data sets that are used, are capturing the topography, but we can always improve that resolution.
Great, thank you. Let's see, we've got a question about how the report considered the confounding effects of climate change and its effects on land cover or forest disturbance on the proportion of precipitation that becomes stream flow in the Colorado River Basin. Is that something that's covered in the report? Is it something that was considered in the report?
So that's a fabulous question, and the answer is we really don't have much in the report that speaks to those sort of land surface feedbacks, and if the land cover and especially vegetation, especially like forest vegetation changing to non-forest or a different type of forest, how that would influence and feedback both climate and hydrology. We really have not dug into that, depending on the type of model, both standalone hydrologic models and some of the global climate models, known as ESMs or Earth system models, may incorporate vegetative changes. It really depends on how those models are set up and run. So some of that, knowledge about feedbacks is implicit in, some model ensembles. but we did not really discuss that issue in detail in the report.
Great. And kind of taking a step back, we've got a great question. What exactly is base flow and how is it changing?
Yeah. So that's a great question. So there are kind of two perspectives on base flow. One is, in looking at the hydrograph, that base flow is basically your late summer through fall winter flow in a system like the upper basin that is dominated by snowmelt hydrology. That base flow is that flow that is modulated much more by groundwater storage and discharge and less by snowmelt processes. So that's, from that perspective, base flow is a relatively small proportion of annual runoff. There's another perspective on base flow, or you could say another definition of it, that was put out in a couple of recent USGS papers that suggesting that 50%, fully half of the runoff or the stream flow in the upper basin derives from base flow. And that definition of base flow is any water that comes in contact with the subsurface, so, and then makes its way through the subsurface to the stream channel. And we do have some, without extending this answer even further, we do have some a section in the report on groundwater surface water interactions that talks about these perspectives on base flow. The question of, is it changing over time? Is base flow being reduced if surface flows are being tipped downward by warming? And I think the answer, kind of in principle, is probably yes, but there's not, really good information, studies that have looked at this specifically. So I think probably base flow would tip downward over time, assuming declines in overall stream flow, but we really don't discuss the trends in the report, and there isn't really the scientific basis to say for sure.
Great, thank you. Let's see, we have a question also about uncertainty. And so the question is about, tools for quantifying uncertainty of current operational models. This question is about what is the best tool, and I don't know that we have specific recommendations about that, but I thought this might be a good opportunity to talk a little bit more about uncertainty.
Sure. Liz, do you want to?
Well, there actually are some, Reclamation has efforts to get a better handle on uncertainty in their midterm probabilistic operations model. And they can speak to it much better than I can. And we talk about it a little bit in the report. But there are, as we describe in the report, multiple sources of uncertainty, from the original data measurements all the way through all of the different steps, the various models that we have just described, up until the point of actually producing output from one of the reclamation system models. So as far as efforts to quantify those levels, I'm not sure. Maybe Jeff has something to say about that.
Yeah, I really don't have anything to add, except, at least for a conceptual overview, I do recommend looking at we've got a little spotlight on uncertainty within the chapter 1, the introduction to the report, and talking about the different components of uncertainty. And so whatever model or other approach you might use to quantify or measure uncertainty, we need to make sure we're looking at all of the different components or sources of uncertainty.
Great, thank you, you two. Let's see, just kind of jumping around topics. We've got a question about mega droughts, and that is, the question says, you mentioned a couple of factoids. 20% of reduced flow is due to temperature, and current drought are thought to be similar to historical mega droughts. Were previous mega drought conditions also associated with higher temperatures?
That is a fantastic question. And the answer is that dry periods are invariably warmer than sort of normal background conditions of whatever century they occur in. Because when you have dry weather, it also tends to be sunny and low humidity and lower cloud cover. And so you tend to have higher temperatures along with. And so what you see when we look at proxy reconstructions of temperature for those same periods, whether it's in the late 1500s or 1100s in which these previous mega droughts occur, we see somewhat elevated temperatures, particularly for the mid 1100s, but not anywhere close to what we have today. So what we've got now is, warmer temperatures that are occurring across dry years, wet years, normal precipitation years. And so you could think of, these mega droughts as having occurred primarily due to natural variability in precipitation at decadal and multi-decadal timescales, with maybe a little boost from temperature, as you always have from drought, but not due to a global warming or warmer period. And now we have, natural variability in precipitation, even moderate decreases in precipitation as have occurred since 2000, co-occurring with a global and regional much warmer period.
Great, and let's see, we've got at least a couple more questions that I wanted to try to fit in. One of them is, given the findings of this State of the Science report, what are the most significant gaps in the science that should be made a priority for addressing over the next 5 to 10 years? And I know that there is a great section of challenges and opportunities for each chapter, and so I thought this might be a good opportunity to kind of speak about that, and also any other thoughts you have on significant gaps in science that could be addressed over the next 5 to 10 years.
Yeah, it really is, the point of the report. What I struggle with, and maybe Liz has a cleaner view of this, is that we identified so many different gaps, and I think of them more as kind of smaller increment gaps, because much of the low-hanging fruit in a lot of these areas has already been picked, and so we've got a bunch of fruit that's higher on the tree, will take more effort. And so I don't see gaps that can be readily closed, you might say. There's a big gap, for example, in between what our current forecast skill is for climate forecasts, so subseasonal and seasonal timescales, and we have very little skill, especially for the upper basin. And if we had the skill of weather forecasts, that would be a huge improvement. But so you could say that's a large gap, but I don't see, from a scientific standpoint, the way to get all the way there. So it's a big gap, but can't necessarily be filled. So I'm not quite sure how to characterize that. So I see lots of lots of things across these different areas we've talked about in the report that would be meaningful to attack and make progress in unto themselves, but will add increments to that larger need of forecasting reservoir storage 6 months, a year, or even 5 years out.
We did spend some time in the report identifying gaps in the data, and especially monitoring networks. And the ones that really stand out are soil moisture and evaporation, and soil moisture in particular because it plays such a big role in the runoff. So there are areas where investments, I mean, it looks like we didn't do a cost benefit analysis or anything, but where investments could have fairly big impact on the quality of the forecasts and projections.
Great, thank you. And we've gotten a few different questions about monitoring, and so I did want to be sure that we cover that a little bit with the short amount of time that we have left. And so one question was about funding for basic monitoring data like SNOTEL or stream gauges to inform many of the models and forecasts. And another question is asking if we can recommend a best approach for how to increase network monitoring. And so, you know, while we might not have specific recommendations, I'm not sure, I'll leave that up to Jeff and Liz. I did think that this was an important topic to cover that we haven't talked quite as much about in the question and answer period, and that is just the importance of monitoring and if there are opportunities there for improving that in the future.
Yeah, so let me highlight one thing that we do call out in the report. There's there's a new effort spearheaded by USGS with a significant federal investment through USGS in what's called their next generation water observing system, and they're setting up pilot basin scale projects across the country to enhance and improve on existing networks for stream gauging and other hydrologic monitoring. And their second such pilot basin is going to go in over the next several years in the upper basin, specifically the Colorado River headwaters and the Gunnison Basin. And so just Google NGWOS if you have not heard about or gotten hooked up with this effort. The leads at USGS are reaching out to stakeholders in the basin right now. Did a kickoff webinar a few months ago in April, and so I think that would be a great way to get hooked in and learn about ways, and help tell folks at USGS what needs are and how to learn how to support those.
Fantastic, thank you, Jeff. Well, we are about out of time today, and there are so many great questions that we did not get a chance to answer. And so we are going to save all of these questions that were not answered. And we've talked about potentially creating like a frequently asked questions resource for our website, but we also welcome you all to reach out to us to keep that conversation going. And so if your question was not answered today, but you wanted to interact with Jeff and Liz to discuss more, please feel free to reach out and we can keep that conversation going. But for now, thank you so much to all of you for joining today's webinar, and to Liz and Jeff for their great presentation and for answering so many of our questions. And remember, you can download the full report and view other resources on the Western Water Assessment website. We will also be posting a recording of this webinar there. I did see a comment that someone had trouble with the link that was displayed on the slide, so we will be sure that is working properly, and we will be sure to send the link to all of you to the report and also to the recording. In the meantime, as I mentioned, please feel free to reach out to us and keep that conversation going. Thanks so much and have a great day.